Hey guys, this is going to be chapter 8 now. Again, a little bit abridged, but this is most of it. But I want to talk a little bit about the sampling methods and the central limit theorem. So this is a really important chapter. This is kind of a pivotal chapter in terms of statistical theory. So at first we kind of talked about um, what is data, what is probability. We kind of put these two things together by making distributions. We talked about discrete probability distributions, continuous probability distributions. But now we're going to talk about kind of how to take this one step further into a little bit of theory, into a little bit of actual real application. If I can get the slide started. Okay, so the first thing we're going to talk about is sampling. So why would you sample a population, right? Well, there could be a million different reasons. Let's just kind of go through these examples here. So the results of a sample may adequately estimate the value of a population parameter, saving time and money. So if you sample something, I might only need to really kind of get, 1% or 2% of a sample or of a population as a sample to really kind of make a good approximation of the population. So it'll save me time analyzing stuff, it'll save me money if I'm collecting data. There's all sorts of stuff, right? If I'm setting up an experiment and I need to pay people to be in the experiment, and less people the better, obviously, while still having a robust sample size and stuff like this. This is why, for both of these reasons, both time and money, why the U.S. Census is only occurs every 10 years. If it was more often, the data collection and the process they go through takes them multiple years to put out the data anyway. So to do this every year would just be impractical. Now, there are things called like the American Community Survey, which do the census, but on a much smaller scale, using more of a sample sort of method, right? So they kind of go into census tracts and take a couple of people, survey them, instead of using the entire population of the United States. So this is going to save both money because it's going to take forever to contact people, figure out all those sorts of logistics. It might actually be physically impossible to find all these people because it's just having people go knocking on doors and stuff like this is just going to take way too many man hours. It's just going to be way too difficult. Again, there's going to be costs in terms of data crunching, in terms of man hours, all sorts of stuff like that. Also, there are cases too when testing or sampling something kind of destroys it. So this is more in the sense of like the way I think of it, at least, like the natural sciences. If you want to understand like pig hearts, you kind of have to wait for the pig to die and then sample it, or you have to kill the pig or something and then sample the heart and kind of figure stuff out. Oftentimes we don't want to just look at the population of pig hearts because we'd have to kill all the pigs, and that's just not right. So there are different reasons why you'd need to sample something instead of looking at an entire population. Most of the reasons is time, money, feasibility, stuff like this. So when you're sampling, you can grab a sample average, you can grab a sample standard deviation, you can do all these sorts of things. In fact, we talked about them in the very beginning when we talked about different types of data and different measurements of central tendency, stuff like this, right? There's different ways you can calculate both population and sample statistics. Now, we're going to talk about something called sampling error. This is just the difference between the sample statistic. So I grab 1% of the US population, I calculate the average income, and suppose through the census, I also know the corresponding population parameter. I can compare these two things. And the difference between these is going to be the error, right? This is the sampling error. This is the error that results in from sampling. So you can look here. Here's a quick example that you can read on your own, but I'm going to keep going for now. So given that there's going to be some error, right, it's super unlikely that what you sample and the true population parameter is exactly equal. Why? Because it's just, there's noise that happens, right? You're not sampling everything, you might just so happen to get, due to randomness, not even selection bias or anything like this, but just randomness, get a different value. So if I sample, some 1%, and then I sample another 1%, and then another 1%, and I do this maybe even 100 times, not getting a full 100 samples, right? But just getting a bunch of different random 1%, I can then make a distribution of these sample means. So each time I'm sampling, I'm collecting a new average. I'm collecting a new average income, a new average height, a new proportion of race or something like this. There's a million different things, statistics I can grab out of the population via a sampling method. I can keep calculating these means, and these means are all individual data points, which now have their own distribution. So I had a distribution of income, and now I have a distribution of sample mean incomes. So now for a given sample size, the mean of all possible sample means selected from the population is going to be equal to the population mean. So if I sample all possible averages, they're all possible combinations of samples, and I look at that distribution, the mean of that distribution is going to be exactly equal to the mean of the population. This is a really important point, and it's a really important theoretical point that says if we do this sampling, on average, the sample average is going to equal the population average. This is used in statistics all the time. That's why when you grab a sample and you calculate a statistic, you can say this is representative as long as it meets certain criteria of being a truly random sample, not having any sort of selection issues and things like this. And this is kind of where confidence intervals come from, but we'll talk about that later. A second point is that there's going to be less variation in the sample mean distribution than the overall population distribution. Why is that? Because if you think about it, if you have incomes that can range from 0 to, let's say, $1 billion, whereas the averages are going to always be pushed towards the middle, right? It's a measure of central tendency. So you're never going to get anything as large as $1 billion, and you're never going to get anything as small as 0. You're always going to have stuff towards the middle, which is going to reduce the overall variation of that sampling mean distribution. And then finally, what's probably the most important thing is that the sampling distribution of the sample mean, so these sample means that we collected, all these 1% samples, that distribution tends to become bell-shaped. Further, it tends to be normally distributed. We know a lot of stuff about the normal distribution. So to have something that can be any distribution, right? Income, it can be, race, it can be height, it can be anything, any distribution, anything that looks as funky as you want, the sample distribution of the sample mean will still become normal, which provides really, really nice properties for us as statisticians. So here's an example. I'll go through it really quickly. But here are about 7 employees and their hourly earnings. So the average population, or the population mean is $15.43 dollars per hour. Now, if we calculate every single sample or every single combination of 2 people, so every single sample of 2 I could possibly pull, right? These are all of the hourly earnings. Here's the sum, here's the mean of each one of these things. Here's the sum of these ones. And if we take, this is now the distribution, right? Or sorry, these means are now the distribution that I'm now considering. Well, great. Now, if I look at the sum of all the sample means about a total number of samples, we get that exact number as we did before. So again, the population mean is going to be exactly equal to the sample mean on average. Further, here's a distribution. You have the distribution of hourly salary or hourly wages. And here we have the distribution of the sample mean. Now, this is not normally distributed, right? But you can see it's more normally distributed than this one. So we'll talk a little bit about this in a moment. So this is where the central limit theorem comes in. If samples of a particular size are selected from any population, and that's a really key thing, any population, the sampling distribution of the sample mean is approximately a normal distribution. Further, this approximation improves with larger samples. This is where we get the magic number that you might have heard of before, that n equals 30 is like good in statistics. We want samples of at least 30. There's really no justification. It's a rule of thumb. We'll see in the next slide that 30 seems to do a pretty good job given a few arbitrary shapes of distributions. But 30 is not a magic number in any sense. It's just a good rule of thumb. Personally, I would always prefer more than 30. I think 30 is rather low, but at a bare minimum, 30 is okay. So here's some pictures of different populations. So we got this weird U-shaped distribution, right? This almost looks like the reverse of a normal distribution. This is the distribution if n equals 2. So we have this kind of like triple humped distribution. N equals 6 looks pretty normal. N equals 30 looks really normal, right? This has a pretty tight variance, right? Pretty small standard deviation, pretty small variance. We have this triangle distribution, and we can see that as we increase our n, we get pretty much back to where we were before. We have this uniform distribution. We can look at the n equals 2 case, n equals 6. Again, it just seems to, as you increase your n, it's going to converge to that normal distribution that has beautiful properties. So here's a really cool website I had found and I was kind of looking at before, but you can take a look at this. It goes through some different distribution or some different examples of how this distribution process works. So if we kind of look at it here, we can take a sample. Here's our sample mean. We can do it again and again. Remember, it's not going to pick these average. It's still going to have less variance as we keep going, right? So essentially what we can do is we can kind of say, okay, here's a arbitrary distribution, right? Super irregular, but it's got something to it, right? Well, what if we just start to sample this and we just look at the distribution that comes if we do it over and over and over again? If we start to sample it, we're going to see that the mean of these sample means is going to kind of hover just shy of the population mean. But as we start to keep going and going and going, you can see it kind of starting to creep to the right to be almost in line with the population mean. And further, you can see it trying to make a normal distribution. You can see this bar here trying to creep up a little bit. It's a little bit flat, a little bit skewed. But as we keep going over and over and over again, if I let this run and run and run, it'll make a really nice normal distribution. Further, we can also start to sample and look at how far off as a percentage of, as a percent error it is from the population mean. So I'm going to click this one as well. And we can see it converges almost immediately, right? It starts pretty off, and then the average is pretty much right on line with quote unquote truth. So you can see here, it's starting to kind of converge to a normal distribution. But this is a really good example. You can check out this website by yourself and kind of go through this and meditate on the implications of this. So some conclusions about the central limit theorem. The mean of the distribution will always be exactly equal. So the population mean is going to equal the population mean of the sampling distribution of sample means. I'm saying mean and sample and distribution like a lot, but try to really meditate on what the words are saying. If you collect this distribution of sample means, the average of those sample means is going to equal the population mean. So while we have this new distribution, the two things we want to know from any distribution is the mean and the standard error. Well, the mean we know is going to be equal to the population mean, but the standard error is going to be a little different. The standard error is going to be the standard deviation of the original distribution divided by the square root of n. So as n grows large, the standard error of the mean is going to be reduced. So the average, how far off you are on average, is going to be smaller and smaller and smaller as your n increases. So we can see that in these pictures, right? This distribution of this is larger than the distribution of this, or dispersion, or the variance, or the standard deviation. And as we get to n equals 30, we have this very, very tight distribution, right? In all cases, it's always going to be smaller. So that's where the standard error of the mean comes in. Now, if you're looking to now figure out, okay, I have this sample mean, right? And I know and I'm trying to figure out like how different this is from a hypothesized population mean. You want to create a z-value, but the z-value is going to be a little bit different. The z-value is still going to be x bar minus, or x minus mu divided by sigma. We're going to change it a little bit. So instead of being x, it's now going to be x bar, because it's coming from a sample. So it's an average. And instead of having sigma on the bottom, we're now going to have the standard error of the mean. So to show you the entire formula, we have this. It's going to follow this normal distribution, but it's going to be scaled a little bit differently. You can rewrite this formula here. Instead of x bar minus mu divided by sigma divided by the square root of n, you can take the square root of n and kind of put it over here. So you can find the regular, quote unquote, regular z value and just multiply that by the square root of n. So you could have x bar minus mu divided by sigma. That whole quantity times the square root of n is going to give you the same exact algebraic answer. It's a little bit easier, I think, personally, when I'm writing it on the board and stuff, but do whatever you prefer. And then from here, once you calculate your z value, the z is always going to be larger, given n is larger than 1, because we're multiplying by square root of n. And as long as n is greater than 1, square root of n is going to be larger than 1. In that case, we just go right back to the z table, find those probabilities using this new updated larger z value, and we can kind of make inference and calculate probabilities from this new z value.